One of the early indicators that a revolutionary new theory of matter was needed was the line spectra of atoms. And of course, this led to the Rydberg Formula, which we discussed earlier in the course. And that formula looks something like this, where the light that's emitted by atoms, especially in the case of a hydrogen atom, could be related to a constant times a difference in the inverse squares of two integers. All right, now one of the things that this brings to mind, and I should indicate that these two things are integers, one of the things that this brings to mind is how can we interpret an equation like this? There's no theory that sort of provides a basis for this kind of formula. The formula is entirely empirical. But one of the things we can get from this, and we talked about this earlier, is that the energy levels of an atom, or I'll say of a hydrogen, are discrete. That is to say, it's not a continuum of energies, because if it were in a continuum, there wouldn't be line spectra. Second thing that we can say about this is that the energies of the atom are proportional to 1 over n squared. Now, why do I say this? Well, if this is the difference between two energy levels, and the only thing that relates to a difference is this difference in 1 over n squared, then somehow those energy levels must be proportional to 1 over n squared, which is a rather remarkable result because there's nothing in classical theory anyway that would indicate the presence of integers in any form. A third thing that raises a question is there's no physical explanation for the value of the Rydberg constant. And that value, at least as it was observed, and I'll put this in a different color, but the value that was observed experimentally was 109,677.6 inverse centimeters. Okay, and so a fairly precise number that was measured, using very good instrumentation for the time. Now, how would one go about explaining these things? Before there was the Schrödinger equation and a real knowledge of quantum theory, Niels Bohr, a famous Danish physicist, proposed a model in 1911. So let me mark that over here. All right, what Bohr basically proposed was that the electron makes circular orbits about the proton. All right, so one could draw that, for example, like this. We could say here is the proton and the electron is just traveling around it in a big circle. So I'll put the electron up here, much like the planets go around the sun. In fact, the planetary model is sometimes what it's called. Now, a second part of his theory is that just as it is the case for planets, some of the forces that are brought to bear on this are Coulomb Attraction and centrifugal force, the centrifugal force forcing it outward. And what Bohr postulated was that these two balanced. So one way we might write that in mathematics would be to say the Coulomb force, which would be written E squared over 4 pi epsilon 0 r squared, is equal to the centrifugal force, which one could write as mv squared over r. Now let me explain what some of these things are. M here is the mass of the electron. So I'll just say m is equal to m sub little e. All right, the r is the radius of the circle that the electron is going around, and the v is its velocity. Now over on the other side, the Coulomb interaction, the E is the product of the charges of the electron and the proton. Okay, and since they're both the same, it's the same amount of charge. This 4 pi epsilon is, the epsilon is a permittivity of Coulomb force in a vacuum, and it's really present here just to make sure the units come out right for the metric system. Okay, and the r squared here again is the radius of the orbit of the electron. All right, so one last hypothesis, and this was the critical one in the Bohr model, is that the electron has is traveling in a wave and it has an integer number of wavelengths in its path. Now, remember that this was done in 1911, so it's before the time of the de Broglie hypothesis. So this was really actually a very stunning sort of conjecture on Bohr's part, and it was ahead of anything that people knew about the wave-like nature of matter. But one might write this conjecture as follows, that the number of the circumference of the electron orbit is equal to an integer number of wavelengths. And later on, we can associate this with the de Broglie wavelength, and it makes it a little bit easier for us to develop the theory to say that this means that it's equal to h over mv. Bohr did not use that particular relationship, but we will in our treatment of his theory. Okay, so this was the Bohr model, and without going into too much detail about the things that it represents, I'll note that this particular condition here indicates, if I move things around a little bit, I can show that mvr is equal to n times h over 2 pi, which is just nh bar. But what is this telling us? Well, mvr is another classical expression for the angular momentum. So it's basically saying that the angular momentum is quantized into integer multiples of Planck's constant divided by 2 pi. All right, so when one applies Bohr's model in all of this, one actually can calculate some very interesting things. First of all, he was interested in what values of the radius would satisfy this condition. And it turns out that you can apply his theory in such a way as to get a direct answer for that. And you get an expression that looks something like this. Okay, h bar squared n squared, okay, n is still this number that we're multiplying by the wavelength, divided by m e squared. And since h bar is equal to h over 2 pi, we can convert this back to the regular Planck's constant as follows. We can just write this as e h squared n squared divided by pi m e squared. And this particular quantity, and you can work out the units of it, comes out to units of length, and we give it the special symbol a sub 0, and this is something known as the Bohr radius. And we'll see that this quantity actually comes up even in the quantum theory of the hydrogen atom as a very important quantity of measuring length. Okay, from this force, from the force balance that we had over here, notice that mv squared is like kinetic energy. So if I want to write the kinetic energy in terms of other quantities, I would write 1/2 mv squared. And if I move the r over to the other side of the equation, it'll cancel with the r squared in the cancel partially with the r squared in the denominator, and I would have that 1/2 mv squared is equal to e squared over 8 pi epsilon r. Okay, well, this, as it turns out, is that's essentially the Coulomb energy. It's 1/2 the Coulomb energy for the interaction between the proton and the electron. So if I write the total energy classically, that's going to be 1/2 mv squared, the kinetic energy, minus e squared over 4 pi epsilon 0 r. That's the potential energy for the Coulomb interaction, but since this is equal to this, e squared over 8 pi, I end up with a value that is equal to e squared over 8 pi epsilon 0 r, okay, for my energy. Now, if I use this definition, if I say, okay, the Bohr electron is at this radius from the nucleus, I should have said something that this is for the case where n is equal to 1. Okay, so if I substitute 1 for integer here, I'll get a 0. Okay, if I substitute that in down here, I end up with an expression for the energy levels that looks like this. M e to the 4th the e to the fourth comes from this e squared plus the e squared that's part of the definition of the Bohr radius, over 8 epsilon 0 squared h squared. And this is all multiplied by 1 over n squared. And I've separated the 1 over n squared so that we can see that this is true for different energy levels of the hydrogen atom. All right, so what this would imply is that all of this somehow contributes to the prefactor in the Rydberg formula. So in other words, somehow this is related to that Rydberg constant. And indeed, if we were to take this number and divide it by hc, and the reason I do that is because the Rydberg constant is basically giving us an expression for 1 over lambda, which is this wave number quantity, then I need to divide by hc because energy is equal to hc times this wave number. Then I would find that the Rydberg constant should be given by m e to the fourth over 8 epsilon 0 squared h cubed c. And it turns out when I plug that in, when I put all the numbers in, I find that this predicts a value of 109,737 wave numbers. Now notice this isn't exactly equal to the number that was observed. So what's going on here? Well, it turns out that the whole, this can be fixed by, instead of using the mass of the electron in this expression, which I've done here, this is mass of the electron. If instead I treat this the same way that we did the rigid rotor and use the reduced mass for the electron, so that would be the mass of the electron times the mass of the proton divided by their sum. And when I use this in the formula instead of the mass of the electron, I basically get the number that is observed experimentally. So this was an amazing success on behalf of the Bohr theory for the hydrogen atom, even though it physically it has some very faulty bases to it. For example, whenever you have an oscillating dipole, which is what an electron orbiting a nucleus would give you, whenever you have an oscillating dipole, it emits energy. It emits light. So it would lose energy and the electron would decay into the nucleus. So the classical theory still was not the right answer, but Bohr had made some tremendous advances in moving us toward the thought of electrons somehow behaving as waves, and it took de Broglie's hypothesis to affix a wavelength to an electron, or to any matter for that matter, to really launch us on the way toward quantum theory.